while we wait for pizza and
Everybody hear me okay? It's a little echoey in here. I've been doing Kubernetes stuff for about 3 years now. Starting at a bank where I sort of was managing Kubernetes migration, and then for the last almost a year at Heptio, where I've been working on upstream Kubernetes, building a bunch of tools using Kubernetes, helping customers use Kubernetes, and I really, really love Kubernetes. So like I said, I work at Heptio. I'm not really here officially representing them now. I'm here mainly to talk about this project, which I just open sourced on Friday. It's called Ironclad. It's basically a demonstration of how to deploy a web application firewall on Kubernetes, sort of like one opinionated way that you might do this. But as sort of a meta pattern, I'm going to talk about sidecars. So like one of the best references for what does the word sidecar mean is actually this blog post from 2015 from Brendan Burns on the Kubernetes blog. And so he talks about some patterns for building distributed systems on Kubernetes. And really the sidecar component, I think a lot of people when they encounter the concept of a pod in Kubernetes, it's a little bit confusing why there are multiple containers in a pod and what use cases that might have. So I think the best way is just to look at some examples of how you use it. And I think depending on your background, I think it has a lot of similarities to the way you would manage kind of traditional VMs or physical machines where you have an application or a couple applications, and then you have like a bunch of kind of system services that are providing a platform for the applications. So your applications expect to have DNS, they expect to have a way to ship metrics, they expect something else is going to take care of their logs for them, they expect that something else is going to restart them if they fail, like there's an init system. And those are all kind of like core, like common platform components that are usually managed by a different team. Usually it's a different team that's running applications or at least writing applications and managing all those kind of platform services. So sidecars, in my mind, the best use cases for splitting out similar kinds of things that are kind of platform features and being able to run them bundled together with an application in a way that they can be really tightly coupled because they interact with each other, but the two components can still be managed by different teams really easily. So some of the examples Brendan goes through really quick here. He calls these sidecars. This is an example where you a Git synchronizer. So this is where you have say one application that serves, it's a web server, it just serves static files from disk, and that's all it knows how to do. You have another container, which is a component that sits out there and pulls a Git repository and syncs down to a local directory on disk. If those are just two completely separate containers, that would not be useful. But one of the neat things about pods is that the containers within a pod can share resources in a really kind of granular way, where you can pick and choose which kinds of resources you want isolated and which ones you want shared. So for this use case, you could choose to have a shared file system mount point between those two containers, so that the one Git container was syncing down into what it saw as a writable directory, and the file server saw a read-only mount point for that same directory. So it's a case where by breaking down some of the walls between the containers, you're able to accomplish something useful. Another example he has here is an ambassador container. So this is sort of an outbound proxy for your application. And I see this pop up a lot. So the idea here is you have, in his example, you have Redis, which is this big data store, and you have a large cluster of Redis instances that you shard. So different requests need to go to different instances. And maybe you have a few dozen applications that need to use that Redis data, and maybe they're written in a few different languages or they run on a few different runtimes. So that sharding logic, about like, if I have a request for this piece of data, which Redis do I talk to? You don't want to go implement it half a dozen different ways for Java and Python and Ruby JavaScript, and Go. Instead, what you can do is pull that out into an ambassador. So the ambassador runs in the same pod as your application. It listens on a local host port. It takes inbound Redis requests in this case. It has a logic then for deciding which outbound, which Redis shard do they go to. So from your application's perspective, there's a local host Redis that contains all the data, and it doesn't need to have any of that logic about sharding or anything like that. And the cool thing here too is, in this case, this is the first example where this application, apologize, let me make this a little bigger. This application is probably managed by an application development team. This Redis proxy is probably managed more like by a data team, the team that's managing the data, the Redis sharding. So that pattern of a ambassador that runs on localhost and provides some kind of complicated network service in a way that's really simple for applications to consume. Another example of that. Yeah, so that's a good point. Yeah, so the thing that makes this possible is another case where you can break down the isolation between two containers. In this case, the thing they share is a network interface and a network namespace. So basically, because these two containers in the same pod have the same local host. So if you have two different pods, they have network namespaces, so they have different local host interfaces. And a container or an application that listens on localhost in one pod is not listening on the same local host as another pod, but two containers within the same pod share that, so you can provide this really easily. I didn't even think about this as an example when I was thinking about this presentation. This is another example of the ambassador pattern, where I've got a container that runs PG Bouncer, which is a Postgres proxy. And the use case here is that you run PG Bouncer in your application in the same pod. PG Bouncer listens on a localhost port. Your application connects to a localhost Postgres with no credentials. And your application doesn't have to know about the database password or what database it's supposed to be connecting to or the host name of the database. It just connects to localhost. That PG Bouncer then is configured to basically inject credentials into the request, to route the request to the right backend database. And again, this is a case where this PG Bouncer sidecar is kind of owned by the same team that owns the Postgres infrastructure, and sort of providing the service of that Postgres infrastructure in a way that's really easy for an application to consume in any language or runtime easily. So that's what Brendan calls the ambassador pattern. The adapter pattern is almost the same thing, but kind of in reverse. So the idea here is you have an application that knows how to, in this case, I think he's talking about metrics, monitoring data, so like JMX or StatsD. StatsD is the one I'm familiar with. So you have an application that knows how to emit data to StatsD, but it turns out actually you're all in on cloud native now. You're all in on Prometheus, so you don't want StatsD, you want Prometheus. So you run something like the StatsD exporter. You run this as a sidecar in the pod. So this is a service that you can set it to listen on a localhost port inside the pod. It pretends to be StatsD. So if you have an application that can push to StatsD, you just tell that application push the localhost. This thing buffers up the StatsD metrics and exposes them as Prometheus metrics. So you're able to basically, he calls it the adapter, because you're kind of adapting the data format or adapting this application to fit to run in your environment. And this is also really, really big, like this kind of pattern in general. I'm going to show my example too at the end. Really powerful if you don't completely own the application. So if you have like internal applications that your company develops and you're pretty consistent, then probably you can just port them all to use Prometheus. But if you want to run, in this case, Redis Redis doesn't know about Prometheus, and you probably don't want to sit down and write a bunch of C code to add Prometheus support to Redis. Adding this sort of sidecar and be a much easier way to do that.
So is that really just like forwarding the...
Yeah, all these things, it's kind of just a little shim sits in there, and again, this is the same trick as sort of the second case where the boundary that you're breaking down here is that they share the local host network interface. The other boundary, so the Kubernetes docs have a little bit about how to share volume between containers. There's also a new feature in Alpha and 1.10 that just came out, which is you can share a process namespace. So the process namespace is the namespace in the Linux kernel that basically it restricts what you see when you do PS AUX. Like when you run PS and you're listing other processes on the system, the process namespace is which processes do you see when you list processes, and it also controls then who you can send signals to. So a good use case for this new feature in Kubernetes is you can sort of have a sidecar that, let's say, loads dynamic configuration from a shared database or something like that, drops it down to disk, and then sends a signal to another container, to a process in another container that signals it to restart, which is a common pattern for a lot of system daemons. Cool. So that gets me to, so let's pause for a second. Any questions about sort of the pattern? Yeah.
So with this, I'm having a problem. I'll kind of give you the motivation here. So I have a node application, it wants to connect to a database, but instead I'll have a node container that has a node application and another container that has a database. So then I have to network them, which is a problem for me. The easy way is to use Docker Compose.
Yeah.
So does this kind of replace Docker Compose? Is that where this fits?
It's not really a replacement for Docker Compose, but it is in the sense that it makes it easier to kind of get applications up and running in Kubernetes oftentimes without changing the application itself.
But the end result is a similar use case?
Kind of. I mean, Docker Compose is more oriented towards like local development, trying to sort of get an environment up locally. This is applicable for that use case tangentially, but more for sort of like the production cluster at a sort of larger scale where you have sort of multiple teams using the cluster, and you might have teams that own different like the data storage layer versus application layer stuff. Yeah, so in this use case, I don't have a diagram of the database case, but the database would be sort of like the monitoring system here is. It would be sort of yet another container that's exposed as a service in your cluster. And so the adapter in this case is embedding, it sort of contains the core implementation of how do you know which database to connect to, how do you present credentials to the database. And that can get complicated if you have things like maybe you need to go talk to the vault to get dynamic credentials, or maybe you need to, you have some sort of sharding scheme, so you actually have to decide based on the query which database backend to go to, or maybe you have failover and you need to be able to send out a signal and flip all your applications from sort of one layer to another, one database backend to another really quickly.
So basically, this reduces the need for all the ceremony for the application developer to know how to connect to databases.
Yeah.
Local host, I want to use you.
Yeah, it's really so. Founder of my company is Joe Bida, who's also one of the Kubernetes creators. He likes to call Kubernetes a platform for building platforms.
It seems that way.
So it's really like this case where, as an application developer, you probably don't actually care very much about Kubernetes. That's fine. What you probably care about is how do I make my app connect to the database. And as a team in your company who owns Kubernetes, you can sort of provide that platform really easily. And Kubernetes is sort of not being opinionated there. It's just giving you the tools to build that platform for internal customers. So the platform interface that the developer sees is, I just connect to localhost Postgres. And you have sort of the domain knowledge to know, like, oh, actually, like I've got replicated Postgres, and you need to be doing connection pooling, and you need to be logging queries, and you need to have client TLS cert set up, and you need to get your TLS cert out of Vault, and all that logic is in a separate container. And the other kind of selling point, I guess, for separate container images is another way you could do this, right? Is you could have one container that had the application source or the application binary, and then another build step where you also add in this proxy, and you add in a little init system that spawns it. But now, sort of every time you change, let's say you change something about the proxy, now you have to go rebuild all your application containers, and they need like a new version number because they're different, even though the application didn't change. So it really is helpful, I think, to think about it as a separate artifact with a separate version. It's kind of bound together at the last possible second when it's deployed together in a pod. Up until that point, it's a separate application.
So without all the tech talk, it'd be easier to say this prevents the database people from needing to talk to the application people. Because application people, all they see is localhost, that's all they care about, and the database people do all the ceremony in their own container.
Yeah. So it's basically a way of like, if you, similar in a lot of ways, if you're on like a cloud provider and you just ask for a database, it's kind of provided to you as a service. You just say, I want a database. Something very complicated happens behind the scenes. You get back a database and you just talk to it. Kubernetes is a really good toolkit for starting to build those kind of services internally that are like API driven, where yes, there's some kind of fairly complicated thing that's happening to provision you like a Kafka cluster or something. But as a developer, all you do is ask for it with an API and you get back a handle to talk to it.
Well, this is how, if you deploy containers onto Google Kubernetes engine and use Cloud SQL as your database, they're like, use the Cloud SQL proxy. I have no idea how I'm connecting to that database. I'm just using, and here's what I thought, these names, the ambassador, adapter node, have those fallen by the wayside? Because they call that sidecar. You call PG Bouncer sidecar.
I tend to call
right?
it anytime you have two containers in the same pod and one of them is not the main thing. I call it a sidecar. This is what you're talking about here, the Cloud SQL proxy. Yeah. It's very similar to the like PG Bouncer thing for MySQL, I think. I'm not sure that the names have stuck for. I mean, people do talk about ambassador, people talk about adapters, but I think of sidecar as a superset personally.
And I'm fine with that.
So cool. So I'm going to get into this. I apologize too if I did give a version of this talk before at DevOps Meetup in Kansas City. The code has gotten a little better since then, and it's finally actually open source. So actually, real quick. If you want to check out the code I'm demoing, this is CryptoLab/Ironclad. Just released hot off the presses 3 days ago.
When you're finished with this, can you post these on the Kubernetes?
Yeah, definitely. So Ironclad is drawn from this unfortunate reality that like the internet is a really unforgiving place to run software, and as soon as you put any kind of web application online, within minutes it's getting scanned for vulnerabilities. And usually in 2018, if it gets exploited somehow, usually you find out because now your cluster is mining Bitcoin or something worse, like you lost your customer data. So a web application firewall is one tool that can help a little. So a WAF is what it's usually called. Have people heard of WAF? Okay, so it's okay, about half. This is basically a proxy that sits in front of your application, specifically your sort of web application. And most of them are kind of rule-based, so they are looking for patterns of bad activity and blocking it or flagging it. They're not the smartest things in terms of, it's definitely possible for attackers to evade them using complicated kind of obfuscation. It's also, they can be a maintenance burden. So especially if you have a WAF that's in blocking mode, it's very easy for it to cause production outages. It starts blocking. If you roll out a new version of your application and the WAF decides that your homepage looks malicious, then like now your site is down. And it doesn't really matter if it's down because your users aren't going to care that it's down because your WAF is there. But it can be a useful tool. I think especially if you make a WAF easier to manage, which is sort of my goal with this. Traditionally, WAFs have been something that you ran as a separate sort of proxy tier, totally separate team managed it from the team that's actually writing the application or deploying the application. And the feedback cycle often for kind of iterating on WAF rule sets and configuration, sort of on the order of hours. You're sort of like think about these text files, maybe rolled out with like Chef or Puppet or something like that, and trying to orchestrate that in a safe way so that if you push out a bad rule set, you're not taking the site down. It takes a lot of orchestration. So Ironclad is just a sort of a demonstration, proof of concept, reference deployment for how to run one popular open source WAF on Kubernetes. So what it is this is a demo I'm giving today. So it's the mod security WAF, which is an open source WAF engine managed by the OWASP project, which is another nonprofit org. Bundled together with the OWASP mod security core rule set, which is an open source set of rules that cover a lot of common attacks. Like sort of they're a known quantity. They're tested on a lot of different applications. They're not perfect, but they're a pretty good starting point. The demo I'm doing today, sorry about that, is going to be running locally on my laptop in Minikube. I'm going to demonstrate using this little vulnerable web application that I took from an example on the Go wiki. And then Ironclad. So Ironclad is a sidecar, bundles together mod security and a little process that basically helps integrate mod security a little bit with Kubernetes, makes it feel a little bit more integrated. And I'll talk about a little bit about what it actually does. So the main things it does, one thing it does is support live reload of configuration via config map. So this is a nice trick in Kubernetes. If you have an application that can watch local disk and reload configuration whenever that local disk, whatever that file changes, if you have that file placed into your pod via config map mount, then whenever you edit the config map, that file will actually update live in all of your pods with some delay. So there's a cache on it, so it takes about 60 seconds. There's a resync in the kubelet. But it's a good way, so you can sort of iterate on, in this case, mod security rule configurations and do that without having to restart all your applications or do a whole deployment. So it adds in useful liveness and readiness hooks. So these are ways to tell Kubernetes whether your pod is ready to accept traffic, whether it's ready to serve requests or not. And what these really let you do is do rolling upgrades, rolling deploys with no downtime. So because Kubernetes can know that it just spawned a new copy of your pod, a new pod, it knows that pod's not ready to accept traffic yet, it won't shut down the old one yet. And likewise for let's do rolling deploys with no downtime in our pod. If it's JSON formatted logs, so the native log security format does support JSON. It's a little bit of secure JSON format. This image log format, but I'll use the index and Elasticsearch and then it also has some Prometheus metrics. demo I'm going to do today has sort of three moving pieces. One is my browser. One is the ingress controller Kubernetes, which takes requests from my browser and hits them to my pod Kubernetes or its service. And then this hello app. So when the request, first scenario I'm going to go through here is it's a request that comes in, it's going to go straight to this hello container. And I'll show that service. And feel free to stop with questions. So this came from this page on the Go wiki that says how to write an application, right? And so I'm a lazy developer. I don't go to the end to copy the working code. I go to the first example that works. I copy paste it into my editor and start running it in production. That's what I do, right?
And security vulnerability.
Yeah. So I got a local cluster up here. This is a neat trick we haven't seen somebody do this before. Running kubectl git across a bunch of different resource types. Watching pick a namespace here that I'm going to demo in, and then I have that whole command running inside of watch. And it just runs something in a loop and updates the screen. Take a little step, get a little dashboard. I'm going to show each of these things to it as I make it. So the first thing I'm going to make is a namespace. This thing running. Next I'm going to load up some certificates, keys that I rebaked.
Let me write this down.
Then I'm going to load config map. Right now this config map is pretty boring. It just says that it's going to be in enforcement mode when I enable it. And then we're going to actually launch some applications here. So let's start with this scenario, which I showed in the diagram where there's just one container. Okay, so there's just one container in this deployment. It's going to spawn one replica. This is the most boring application. It's going to listen, in this case, on all interfaces on port 8080. And like I said, this application here is from that wiki, basically put together. Not much to it, but it's sort of a wiki. That's the example app that they're showing you how to build. It's a very simple wiki. Okay. We're going to put a service in front of that so we have something to target from ingress. So this is a service that points to all of the pods labeled app equals demo, and points to them on port 80, or points to them on their HTTP port that it serves on port 80. That service was called demo. So then I have this ingress which says, hey, here's this host name. Whenever you get requests for this host name, drop them to the service name demo on the HTTP port, and also set up TLS termination at the ingress. Now that I got that, go to my browser here. I've got a wiki. I can write, this is the food page. We can write hello world. It's bigger. Save that. And now I just edited the food page. I can do that to whatever other page. I can edit the bar page. Bar. And now we're going to get to the fun part here. So what if so let's go back and look at the source code here. So when I said hello bar, you notice that my message ends up in the HTML of the page. Not a surprise. All right, instead do something like that. Looking to find out whether the example app correctly escapes HTML or not. Spoiler, it doesn't. Right? So when I do that, my JavaScript fires and you get the alert. And this is sort of I always think this is a really bad example of a cross-site scripting payload. Because people see alert 1 and it doesn't seem very dangerous. But in a sort of a real scenario, cross-site scripting payloads can steal customers' data, they can keylog passwords on your site, they can do all sorts of bad stuff. Okay, so now we're going to show the version 2. So we're going to comment this out. You go down to the fixed version. That runs Ironclad. So in this case, we still have the vulnerable application, but now instead of listening on all interfaces, it's only listening on localhost. We run Ironclad. We're pointing at a configuration file that we're going to put there via config map. It's going to listen on port 80, and it's going to proxy requests to localhost port 88. So it's going to basically accept requests. I'm going to share this. So it's going to accept requests from ingress. It's going to do this sort of filtering, and it's going to forward them to the local application. And all that time it's going to be watching this config map for preview config. So we can apply that and watch Kubernetes do a rolling update here. So if you watch the pod up at the top, you can see got a new container creating. Now it's running and ready. So the old container is shutting down on that. Always impressed by how fast it is. Okay, so the app still works. We still save. And now let's try to do our little attack again. Instead of getting an alert, now we get this 403 provision, which means that the request was blocked. The vulnerable application never actually saw that request. It blocked out the proxy.
So the alert actually got into the database, and then they tried to write alert, and got it blocked out.
Actually, even before it got to the database.
Okay, so it does filter the input.
Yeah. It can filter inputs and outputs.
Okay.
So there's certain rules that apply on output that look for things that will be vulnerable. There's different patterns that apply in both directions.
So it's beyond the scope of the lab to escape that. So you implement that in your app, and if it fits by whatever escape you can put in your app, then that's what the lab is.
Yeah, so
For this particular app.
in this case, like a script alert 1 probably wouldn't trigger a rule on output, because if you had rules that trigger on that, they would probably false positive on a lot of HTML.
Or you could do a rule that says within this div, if you see HTML,
Yeah, so an example of a rule that they have in the core rule set is looking for things that are common in the output of SQL injection. So if you SQL inject, usually you get the thing you're looking for plus a bunch of junk. And a bunch of junk will be formatted the way the database would format output rows. So you can actually alert on data that looks like that. It's not from the main figure out. Another example is, so this isn't in any of the default rule sets, but people run credit card number filters. So if you have, credit card numbers follow the pattern and the check digit, you sort of look for them. So if you know your application is never supposed to print credit card numbers back to the user, which it probably isn't if you're PCI compliant, you can say, hey, even if somehow my app is handling credit card numbers internally, I don't ever want one of those to end up in HTML output. So if one does, like that's an error blocking. So here we can see the logs from that request happening. So here's Ironclad starting. Here's one of the JSON logs. It says, apologize, this is a bunch of JSON, but the payload here is cross-site scripting attack detected via lib injection. And from that, you can also see then the user agent that made the request, the IP address, and this can potentially give you clues about what kind of what kind of activity generated that alert. Cool, so now I'm going to show another feature here, which is the live view. So we're going to go edit this config map. This is a section of the config in Ironclad that lets you append rules to the core rule set. So these are the rules that basically change the default action. Change it from a 403 error to a redirect. So if we apply those rules, we're going to sit here and it's going to be painful, but we're going to wait for Kubernetes to see our config map change and apply it to disk.
Aside, is cable alias or something? Or?
Yeah, let me show off Kale because that's the trick. Kale is a tail for Kubernetes. It's a little bit better. So there's control logs has -F, and you can watch logs that way. Kale is an extra feature you get in Kale is it can watch multiple pods at the same time, multiple containers in a pod. In fact, you can use it like I did and just say, show me those live logs and everything in this namespace. Pretty handy. I'll link that in the chat too. Okay, so we see the Ironclad process here said it's reloading Nginx. That's because it noticed that file change. So now we're going to go back and try and do the same attack again, but now we expect the redirect to happen. No, it didn't autoplay because I'm on a Chromecast. Yeah. There we go. So that's Ironclad. That's all of my, that's my talk. I made a chat more about Ironclad or about like sidecars in general or patterns other people have used.
I was curious about the after sidecars. So you usually see, I guess I can see what's going on with like that fix that then like to be fixed later instead of having to get after running something because that could be pretty expensive. Yeah, I think it's actually so is that property schemes?
Yeah, it depends. Like one of the pressures, like you said, like resource usage wise, I think it's actually not necessarily costly to run things out of process. A lot of these things like PG Bouncer, these are pretty efficient processes. They don't. If you have a sidecar that's written in like a larger runtime, Java or Ruby or something like that, then there should be a pretty significant memory cost to have a sort of a second routine or a second Java process. But a lot of these things are in Go, C, or things like that that really don't have a huge runtime in terms of memory. So I think in this case, I didn't have any memory request or limits, but this thing would run in sort of like 64 megs of RAM or something like that, and not a lot of CPU either. So, but like you said, it is one cost. If you want to do the same kind of adapter pattern, but you want to sort of move that into your application, that works well if you have a relatively consistent set of applications that are written. So you could write like a shared library, right? That you link a package that you link into other applications to do something. In a lot of ways, the sidecar pattern is like a shared library put out in process. So you could write this shared library in a different language, and you can share the same shared library across your Ruby and Python and Node and Java apps.
Yeah, like the investor just seems really cool.
Yeah. Would Istio being an
Yeah,
example?
so Istio, if you're not familiar with, Istio is a service mesh. So it's a proxy that kind of fits in the kind of like the ambassador and adapter roles. So it actually proxies inbound requests to your application go through are terminated in Istio. It forwards your requests to your application locally. Also, outbound requests from your application go out through your envoy. And sort of it links together all your applications and does layer 7 smart stuff. Right? That's the idea. It's doing sort of fancy routing and things that, again, like if you were Twitter, for example, Twitter implemented a smart RPC library, which is an enable that they run. It's a JVM library, and it does all kinds of fancy things like circuit breaking, where you have an application that has an upstream dependency. That upstream dependency starts to get really slow, and it starts to fail. At some point, you just want to stop trying, right? You don't want all your requests to get slower, so it's better to just disable that. Trip the circuit breaker, have that feature be disabled for a while. Other things like smarter load balancing that can mutual TLS or like secure encryption between different hosts, metrics, logging, all the kind of like things that you would want your RPC library to do. But that kind of finagle model is hard to port to an environment where you have a dozen different languages and runtimes. Okay? So now if you want to have that finagle, but you want a Python version, a Ruby version, and a Node version, and you want a Java version, a Go version, and a native version for C, you're stuck implementing all these different implementations of the same thing, and they're probably going to be inconsistent and of varying quality. So Istio is the idea that you take that kind of the things that you want out of your RPC system, move them out of process, and run them as a sidecar. Another kind of interesting thing that Istio does in Kubernetes.
There was a question.
Oh, sure. Real quick. Yeah.
Well, so in the deployment, it seemed like it was very much an opt-in to use the sidecar.
Yeah.
Is that?
Yeah. So in this case, yes. Some patterns for that. So one thing is, in some companies, this is how you could roll this out. That maybe the application development team or the application operation team that's deploying that application is actually the ones responsible for making sure that it meets security policy. That's one scenario. Another scenario is if you have a cluster admin who is the one responsible for making sure that all the applications on the cluster meet security policy. You could use something like pod presets. These are actually opt-out, but this would basically give you a way to say, by default, every application I run gets the sidecar injected into it. So that's one of the use cases for pod preset. If you want sort of a stronger enforced version of that, there's like mutating webhooks and admission controllers. You could say, hey, actually for this namespace or for these users, they're not allowed to create pods unless they have this thing injected into them. So one thing I do like though about having that brings back to like this trade-off where another way you can manage math is to run it as a separate service at the edge of your network, and say every request that comes into my network goes through the WAF there, and I know that I don't have to worry about it for individual applications. The thing I found with that model is that the WAF config ends up with lots of special cases that are tied to individual applications. So you might need this compatibility thing where this version of this app needs this tweaked rule, and so your WAF configuration gradually accumulates this pile of special case rules, and you're never quite sure whether you're done with them or not. So it gets more and more complicated. So with this model, you still have those special cases, but now they're in the WAF config for this application and for this version of this application. You can kind of manage the complexity bundled together with the application deployment instead of in a central place. I was going to mention too, one thing that Istio takes advantage of in Kubernetes is that different containers within the same pod can run with different privilege levels. So Istio needs to be able to do the thing it does. It needs to have I forget which capability, but basically it needs to be able to control IP tables on the network namespace inside the pod, which is like a privileged thing that normal applications should be able to do. But because you can run the Istio sidecar container in privilege mode, the application is not in privilege mode, you can sort of, it's able to set up IP tables correctly on your application and write that.
So with this, would you see a possibility for application teams to manage their own WAFs, but also incorporate like a CI
previous production environment where we managed a real WAF, that was not possible. You got to find out whether the WAF tweaks worked when you deployed to the shared dev that had the WAF running.
Plug and play.
Yeah, I mean, you could get similar capability here with Docker or something like that. The tool, in this case, Kubernetes is actually not the magic bit. It's actually the containerization and being able to bundle these things together. And I think that's a good spot to end because that was just something to walk in.
Awesome. So yeah, I hope it was a good presentation. I will watch it on replay. But pizza is here, so thanks everyone. Enjoy, and feel free to sit around and chat.